Okay, let's continue our discussion of those quadric surfaces. As I said, that we do not really ask you to remember the correspondence between the equation and the surfaces. But for some of those special ones, it's better to have some sort of idea of what the equation is representing. Otherwise, it will have some difficulty in processing those solids, especially their special shape of the solid, and the edge or surfaces are prescribed by those quadric surfaces. For example, this one is supposed to be a cone, all right? And how do you visualize those cones? One thing you could think of is that you always want to start with something you're familiar with. Remember, x squared plus y squared. If you have a constant positive value equalized to x squared plus y squared, then we would know it is representing a circle in xy plane. But obviously, we're talking about equation and points in 3D, then you can see what this means is that at a different height, you have different size of a circle. Okay, so then at a very small z, and you have really small circle. At a high value of z, you have bigger circle. Then it is pretty much a cone kind of shape. Okay, so one more example, which is plotted over here. So what's the difference between this equation and the equation we just wrote down a moment ago? So it is a z squared over 2 equals x squared plus y squared. How do we compare those two? The one on the left and then on the one on the right. And the figure, the surface in the middle, is actually corresponding to the equation on the right. So still, we got a circles, right? We got a circle, x squared plus y squared at different height of z. The whole thing is giving us the radius of the circle. All right. So if we absorb everything, just think this is a constant. Also, this is constant. What's the difference? So to have a same size or same R for a circle, you can see you sort of have to have a bigger z value for the right equation compared to the left. Okay, so what you should imagine that the difference between those two is that the cone is sort of a stretch for the right side of the equation. You stretch this cone a little bit upwards. Just imagine that you're manipulating those surfaces. So those are interesting things to think about and to make connections between geometry and the mathematical formula. It's a bit of fun to think about. Okay, so there are other types of surfaces you might want to remember or have some sort of visualization in your mind. And those kind of surfaces are what we usually see in the almost last part of this course. But I guess when we really need them, we have to come back to look at it. And for now, we want to particularly discuss something that is related to so-called the cylinder. The cylinder are usually just those quadratic equations involving two variables. Okay, so they are becoming a plane curve. The third dimension is not restricted. So, for example, over here, if you look at this example, x over 2 squared plus y over 3 squared equals 1. What kind of shape this is? This is an ellipse. Ellipses are in the do two-dimensional space in the XY plane, right? If you plot it on XY plane, well, this is the X, this is the Y, and when Y equals 0, X has to be 2 or positive, negative 2. It is those 2 points. When X equals 0, Y will be either 3 or negative 3. Then the ellipse is sort of like this one. All right, if we look downward in the XY plane. But this is equation involving X and Y only. But if there's a restrict or vision into three-dimensional space, which is that what we really talk about is X, Y, and Z, and we do not really restrict the choice of Z. And then what we can see is that we are having this ellipse in the XY plane. Because Z is not restricted, then what we are actually forming is a cylinder. So this is representing the cylinder, here the surface. And then similarly, this is a cylinder that the X variable is not restricted. I guess we would have something. So X, so where is X? So this is X, this is Y, this is Z. And for example, we would have a cylinder like this. Okay, so those are interesting thing to look at, and there are different ways to generate the cylinders. And for example, the left panel here, I think it is x squared minus y squared equals 1, and the right one over here, I fitting it is sort of a y equals x squared because z is not restricted, and so on and so forth. So those are the interesting thing because when we write down those equations, if you only think about the xy value in the xy plane, they are curved in the xy plane. But if you're thinking about it in 3D, they're linking to a three-dimensional surfaces. And the fact that they are missing the constraint on the third variable is telling us that we can sort of grab this curve in a plane out to the third dimension to make it a cylinder. All right, so those are the interesting things we should get familiar with. And then after the general discussion of all those quadric surfaces, we want to answer the question, how do we find the trace of the surfaces and the intersection of different surfaces? For example, we want to parameterize the intersection of what? Of those two surfaces. By the way, what this is? This is a plane, right? We didn't write it in the standard form of plane equation, but if we do, we should see this is, if we move the 4y to the left, so it's a 4y plus z equals 7. And the normal vector is 0, 4, 1. Okay, so this is a plain equation. If you write it as z equals 7 minus 4y in 3 dimensions, this is a plain equation. Okay, for this one, I can tell you it is a so-called of the paraboloid. Okay, you can just imagine that because x squared plus y squared is positive, well, it's non-negative, and you add 2 to it, it's always positive for z. Okay, so z, and z has a minimum value of 2. So how do you imagine? At a different height of positive z, you get a different radius for x squared plus y squared. So this is a paraboloid. You can sort of imagine the shape look like this. And this is 2. Okay, so so how would you parameterize the intersections of those 2 surfaces? Okay, so what is the intersection? We have to answer that question. The intersection in terms of geometry is a collection of points on both surfaces. Okay, and in terms of the mathematical formula and the coordinate system, those points with coordinates x, y, z satisfy both those 2 equations. Equation 1, z equals 2 plus x squared plus y squared, and the second one, which is z equals 7 minus 4. All right, and then what do we see over here is that we want to solve for those x, y, z such that both those 2 equations are satisfied. So how do we proceed? Obviously, it is relatively easy to see. We can match the z on the left hand side, so it becoming 2 plus x squared plus y squared equals 7 minus 4y. Okay, and how do we proceed? I guess we can manipulate this a little bit because y squared is here, y 4y is here. We can write this as well, and also there's a 2, right? The 2 is constant. We can move it to the right. So we do this. We add a 4y, and then we also subtract, and to subtract 2. So what do we get here is x squared plus y squared plus 4y equals 7 minus 2. And then there's y squared plus 4y. We want to complete the square, so we make it plus 4 and also plus 4 here, because we have to, whatever operation we do, we got to do it on both sides. Then we got x squared plus, so this is becoming y plus 2 squared. And on the right, we got, well, we got 9, I think, which is 3 squared. Okay, so now this is the intersection. We want to parameterize. So how do we parameterize this? Well, we want to use one parameter, one single parameter to represent all the points that that satisfy all those this equation. The idea is more or less like we sort of have to use the so-called the trig identity. I don't know if you guys remember, but what is a sine squared t plus cosine squared t? This is the trig identity we have to remember. It's constant one, right? So if we multiply 9 to both sides, we got what? We got 9. Okay, so now you can see the idea is that we can parameterize this square and this square, and this becoming equals 9. So what we could imagine, just as we discussed a moment ago, is that this x squared is what? This x squared is something related to the sine or cosine. So I guess we have to work on this a little bit, because this is a 3 times sine t squared plus 3 times cosine t squared, and this equals 9. So if you look at a discussion in the in this square, we can see we can make this more or less just how about we let x part to be 3 cosine t, this part to be 3 sine t, and then we got this, right? So the idea is x is 3 times cosine t, and y plus 2 is 3 times sine t. And here, obviously, the t is chosen from 0 to 2 pi. It's 1 period. Okay, so with those two, we can see the actual parameterization we are looking for is x equals cosine t, and then y equals negative 2 plus 3 times sine t. Okay, and then z equals what? Because as we said, the interception is the collection of the points that satisfy both 1 and 2 equations, and from those 2 equations we derive the relationship, and we can sort of represent them using those 2. But the third variable z also has to be enforced. We can obviously use the second equation there to write down or parameterization for z, which is 7 minus 4 times negative 2 plus 3 times sine t, which is 7 plus 8, which is 15 minus 12 times sine t. And obviously here we have to restrict the value of t, so it goes through 1 full cycle. So this is what we can do. All right, so let's look at another example. So how do we find the parameterization of those two? So this is a cylinder, right? This is a plane again. And from those two, we can see the cylinder could be written as x over 2 squared plus y over 3 squared equals 1. All right, and then we have 2, how about let's write them in different place. So it's 4z equals 2 minus 2x plus 3y. All right, so z equals 1/2 minus x over 2 plus 3y over 4. So by using the similar argument, we can write this as cosine t, and this is a sine t, and cosine t squared plus sine t squared equals 1. So this is a trig identity, right? So x over 2 is cosine t, and y over 3 is sine t. With those two, we realized x equals 2 times cosine t, y equals 3 times sine t, and z equals 1/2 minus x over 2 is becoming 2 cosine t over 2 plus 3 over 4 times y, which is a sine t. So now we have the prime translation. This is a different color. X equals 2 cosine t, y equals 3 sine t. Z equals 1/2 minus cosine t plus 9 over 4 sine t, and t is between 0 and 2 pi for one full cycle.